So now that we've talked a little bit about the fundamentals of streams, let's start to do a deeper dive into common operations in streams. And we'll talk about operations that are used to create a stream first, and then we'll talk about aggregate operations in a stream that do various processing or filtering or termination of the stream. So we'll start by talking about just a handful of stream creation operators. There's actually a whole bunch more we'll talk about later, but this is just to get the ball rolling. So if you're familiar with the Gang of Four book, you probably have been introduced to the so-called factory method pattern. And the factory method pattern is basically a pattern about how you create stuff. And just like people often say, you don't want to know how the sausage is made, or you don't want to have to know how legislation is made, but you just want to be able to be the beneficiaries of the yummy result that comes out of that. Same thing is true with creating objects or elements or other things, streams, for example. So the details of how this is all done is hidden from you, and you can simply use factory methods to start things off. So we say stream.of, and we can give a bunch of strings. So that would be one example. And the way to look at this under the hood is the stream.of factory method converts an array of elements of type T, which in this case is strings, but it could be whatever, into a stream of type T. So now we have a stream, which is different from an array, as we'll see. There's a large number of factory methods that are provided in Java streams that can be used to create streams. And we're going to talk primarily about these, in particular stream and parallel stream. You'll also see some examples here and there with split as stream and of. We've taken a couple look at of. The thing that's kind of the workhorse under the hood that does a lot of this stuff is called the stream support.stream method, and it uses something called a splitterator. We'll talk about all this stuff later. These are the key methods we're going to focus on in this course. Whoops. There's also a pile of other methods which we won't talk as much about. We might even skip over them because they're interesting, but you don't necessarily need to know all those gory details in order to be able to do the assignments we're going to do. But just be aware that there's a lot of factory methods to make streams. Aggregate operations, as I alluded to earlier, perform a behavior on elements in a stream. And this is part of this behavior parameterization thing we talked about before that's so cool. Behaviors are implemented by lambda expressions or method references that correspond to a so-called functional interface. What is a functional interface? A functional interface is an interface in Java that has at most one abstract method that it doesn't inherit from Java lang objects. So a good example of a functional interface in Java would be predicate, which has a single method called test, which takes a parameter of type T, which is a generic parameter to predicate, and it returns Boolean, true or false. There's other functional interface, and predicate gets used for things like filters, the filter operation. There's other operations that are functional interfaces in Java, things like function, which has an apply method that takes a parameter of type T and returns a parameter of type R. So it has a method called apply. So there's function, there's also consumer and supplier. And if you need a recap on some of these things, please go take a look at my YouTube channel on functional programming in modern Java, which goes through about 5 of the most common functional interfaces that we're going to run across. So function is used for the map operation in Java streams. So these are examples of how things are passed as behaviors. Here's a very simple example. So you can see here we're going to pass the capitalize method reference, which I'll show you the implementation of this in just a bit. We're going to pass capitalize to the map aggregate operation. And that will then apply the capitalize method to each element in the stream to consistently capitalize them. And you can find the code here. So you can see here, this is an example of applying this. So we have lowercase Horatio becomes uppercase H Horatio. Hamlet remains unchanged because it's already got the first letter uppercase. Some aggregate operations in a stream will perform the behaviors that they're given on every element in a stream. And that's what's typically called run to completion. So it runs until it's done processing all the elements. Other aggregate operations perform the behaviors on some elements in a stream. And these are sometimes called short-circuiting operations. So they don't go the whole way. And there's really good reasons not to do that. So we'll talk about operations shortly, things like limit or skip. They don't look at every element in the stream. You can think about aggregate operations in a stream as forming a pipeline of processing phases that the data flows through. And this is very much like a water filtration system that you might see in a house or in a place of business where you want to filter out different kinds of impurities as the water flows through the pipes in the system. So another way of saying this is that the output of one aggregate operation becomes the input into the next aggregate operation that's part of this. Java Streams supports pipelining of aggregate operations using a technique or a pattern called fluent interfaces. Read more about fluent interfaces here at this link. Very, very popular technique that's used in all kinds of languages now. And basically, another way of looking at this is method chaining. You basically chain the methods using the dot, so the output of one method then just becomes the input to the next method, and you just chain them together in a nice, fluent way. So here's just a quick recap of how we're putting together these operations in a fluent way. So the of operation creates a stream from an array of elements, and then we fluently chain that to the filter operation, which is an aggregate operation that returns a stream that only contains the elements that match the predicate, only contains things that have h, either lowercase or uppercase h. We then chain that together with the map operator or operation, which will go ahead and return a stream that consistently capitalizes the characters in the stream elements so that they're consistent. Then we chain that together in a fluent way with the sorted aggregate operation that orders the elements in the stream. And then finally, that is given to the for each terminal operation, which is an aggregate operation that performs an action on each element, which in this case is. So again, you just kind of get the sense of like, water flowing through filters or things going through a pipeline, and each phase gets a chance to do something, either creating it, transforming it, filtering it, or doing something to get it all working together. Yes, sir. Yes. Yeah, so all the things you see here are aggregate operations. Some of the ones like filter, map, and sorted, those are so-called intermediate operations. And then things like for each are the terminal operations. So the question basically was, is sorted an aggregate operation? And yes, it is. Yeah. Good question. So the question is we talked about split, apply, combine, and what's filter's role? So filter isn't really splitting anything. Filter is just removing stuff that doesn't match the predicate. So it's applying a behavior and only letting things through that match. So it's not actually splitting anything. It's just not letting stuff through. It's like a bouncer at a club. If you don't have the right kind of shoes on, or they won't let you in, or whatever. If your ID doesn't match the age for the club, you can't get in, or something like that. Now, something to note here, and if we have time, we'll talk about this particular topic, the difference between internal iteration and external iteration. Most of what you've done with Java up to this point, most likely, is external iteration. For example, if you have a for each loop that iterates through every element in a collection, that's external iteration. The iterator is external to the collection that you're iterating through. Other examples would be the Java iterator interface and the way you use it with things like dot iterator and then has next, the next, and all that good stuff. Those are examples of external iteration. And there's certain benefits to external iteration, namely you get very fine-grained control of whether you want the iteration to continue or not. You can break out of a for each loop anytime you want. You can stop calling has next or next on an iterator anytime you want. So you get great control over it. The downside is that there's extra things you have to do, and you have to make sure you do the right calls. So Java Streams uses something called internal iteration. And there's actually iterators working here that are making all these things happen. They're just hidden from you, and you don't see them. And the benefits that come from this are you have fewer accidental complexities. You won't forget to iterate. You won't forget to increment the iterator, for example. And the second thing is Java can provide for transparent optimization. In particular, we can go from doing a sequential processing of these steps to a parallel processing of these steps with really very little change at all to the structure of the program. It just runs faster in some cases when you have the right amount of data and the right amount of cores and the right amount of processing and so on and so forth. So internal iteration is something we'll talk about later if we have time, but it's what differentiates Java Streams from traditional ways of iterating through things in classic Java. Here's how we could have written this code the old school way. So this is the way we do it with Java streams. This is the way we do it with kind of the old school loops and if statements and control flow constructs and so on. So you can see here we would say, I want to make a new linked list of Horatio, Laertes, Hamlet, blah, 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 all the various characters in Hamlet. So now I have a list of strings. And then I'm going to use a for loop, and for I equals 0, I less than the size of the loop, I'm going to say if lowercasing the next element at this location does not yield an H, either lowercase or uppercase, then remove that element from the list. Otherwise, capitalize the element, set it into the list, and increment the count by 1, the loop counter by 1. And after we've done running this loop, then we're going to use the sort operation from collections to sort the list. And then when we're done, we're going to use a for each loop to iterate through the list that remains after removing the elements that don't match, and we're going to print the results. So this would be an example of external iteration, whereas this is an example of internal iteration. Yeah? Great questions. The question here is this sort of old school way of doing things more efficient than this new school way of doing things? Assuming we're using sequential, yes. So for sequential, it's likely that this code might run a little bit faster for sequential code. It probably won't be drastically faster, but it will be faster. And the reason it'll be faster is there's just more stuff going on here behind the scenes, as you might expect. For example, we're building up essentially a linked list of these aggregate operations, and when the terminal operation is hit, then everything starts. So there's some additional bookkeeping information and a few extra data structures and so on. However, the great part about this is once we are able to turn on the parallel feature, which of course is the main focus of this class, since it's a class on parallel functional programming, then you get this massive speed up with little or no extra work. I mean, there's like, you change stream to parallel stream, right? So what could be simpler than that? Conversely, try to take this code, which uses the accumulator anti-pattern, trying to make that run in parallel. Wow, what a lot of work, right? You'd spend probably days trying to get this to correctly parallelize, whereas with streams, it takes you about 20 nanoseconds to change stream to parallel stream. So the real win is in the ability to take advantage of processing. And that's a key theme. If you recall, we discussed earlier when we were talking about the motivation for going from concurrency in Java to parallelism in Java. We talked about the fact that historically we've been getting ahead of ourselves in the ability to create processors with lots of cores, but the actual speed up hasn't really kept pace with what we would have hoped, given all the cores we've got. And so a lot of the motivation here is to make it easier to write code that will enable us, developers, to take advantage of those cores rather than see the performance peter out very quickly. And that's because we're shifting, the whole concept behind this shift is a shift from task-oriented parallelism to data-oriented parallelism. And data-oriented parallelism has this wonderful characteristic that if you can split the data up into many small chunks and then run them all in an embarrassingly parallel way with abstractions like parallel streams, life becomes much easier to optimize and scale. The other problem with this, leaving aside the whole performance set of issues, there's just so many more opportunities for accidental complexities to bite us, right? Because you might get the loop counter wrong. Anytime you have an index-based for loop or while loop, what a pain. You're making all this stuff is just sort of random gobbledygook. It's really hard to tell what's going on. Now, of course, if you don't understand stream syntax, this is hard to understand too. But once you understand stream syntax, you can actually read this code linearly from top to bottom and know what it's doing. You can say, give me a bunch of characters, filter out the ones that don't start with H, capitalize them, sort them, print them. You don't have to sit there and play compiler in your head. Whereas with this code, you have to say, okay, for I equals 0, I less than L size, do this stuff. And you have to kind of think in your head, what's happening? The iterations are going. Am I remembering to increment this every time in the right place, right? It gets very, very accidentally complicated. Okay, so that's the end of our discussion of common stream operations that the Java Streams framework provides. There's lots more, of course, but this is just some of the most common ones.